Okay, building on some of the stoichiometry review we did in class, I'd like to go into a little review of some of the stuff we did with solutions and solution stoichiometry from that. And so looking through this, a lot of this is going to have to do with molarity. Okay, and as we approach this problem here, I just want to remember that molarity, what we're looking at is that's a measurement of concentration for solutions, where it has to do moles of solute, the stuff that's dissolved, moles of the solute over liters of solution. Okay, and so in this case you've added water as your solvent, and so overall we're adding it to a total volume of 244 milliliters. Okay, so to be able to determine the molarity here of NaCl, we need to know how many moles of solute you have. Well, that's great. We have 32.6 grams of NaCl. Okay, 32.6 grams we can convert to moles, and if we do that, we see that that is about 558 moles NaCl. And total volume here, so we're talking about liters of solution, so we have milliliters. We can convert to liters by moving the decimal place over 3 places. So that would be 0.244 total liters of solution, and so our molarity in this case would be 2.29 moles per liter. Okay, for our NaCl. Alright, the other thing we did with solutions, we looked at dilutions. And so with dilutions, what we're doing is we're adding, so when you change the volume of a solution, what happens to the concentration, what is it when it ends up? Okay, and we derive this. So we by rearranging molarity, moles over volume. Okay, rearranging that. If we wanted to figure out how many moles we have, that would be molarity times volume. Okay, and so as we do that, if you add water to a solution, what you don't change is the number of moles of solute that you have. If you have NaCl floating around in solution, adding water doesn't change how much of it you have. And so in that case, you have a certain amount of moles in the beginning. You have a certain molarity and a certain volume that goes with it. Okay. As we add water, as we change volume, okay, you're gonna see that you have a new molarity when you get a new volume. Okay, and so with dilutions, what I mentioned is that you don't change the number of moles that we have. So this moles and this number of moles are equal; those don't change. So if those are equal, therefore we can see that M1V1 will be equal to M2V2. Okay, and so that helps us out. It can always be used for dilutions, whether you're looking for a new molarity or what volume you would need to get a different molarity in terms of your dilution. Okay, but since what we looked at there, this part of this derivation, what we required was that moles were equal. Okay. We can use it sometimes for solution stoichiometry. The only time we could do that for, let's say we're talking about two reactants that are in solution form, like a precipitation reaction, what we need in that case is for moles to be equal. And so to get moles equal, we have to have one-to-one stoichiometry. Okay, and frequently with the type of reactions that happen in solution, and frequently you do actually get one-to-one stoichiometry in those. Okay, we can use molarities and volumes as kind of conversion factors, and so to relate it to stoichiometry like what we've done before, 1.4 grams of magnesium reacting with HCl. Well, the first thing we need for this is a balanced equation. So magnesium and hydrochloric acid gives us magnesium chloride and hydrogen gas. Okay, and to balance that, we need 2 HCl's for every 1 magnesium. Okay, so 1.4 grams of magnesium. Okay, and again, for a lot of these too, since it's a review, I'd like you to try to do this on your own and then check what I'm going to do right here. So go ahead and pause it here for a second before you give it a try. And then when you're done, here we go. 1.4 grams of magnesium. So you need to know that 24.31 grams of magnesium is in a mole. Okay, mole of magnesium. In this case, you know that for each mole of magnesium, you're going to need twice as many moles of HCl. Okay, and so that if we were to stop here, we would have moles of HCl, we have molarity, and we're looking for volume. Okay, so we're looking for the volume that's required to get enough moles to completely react to 1.4. Okay, so if we have molarity and we have moles, we can see that volume would be moles divided by molarity. We could do that in another way. So 0.45 molar HCl, that means 0.45 moles per liter. That means 1 liter of HCl would have 0.45 moles. 1 liter of HCl is equal to 0.45 moles of HCl. Okay, if those are equal, we can use that as a conversion factor. 2 moles of HCl on the top, so moles of HCl will be down here. So 0.45 moles of HCl would be equivalent to 1 liter of HCl for the solution that we're talking about. Okay, so then for this solution to use up the 1.4 grams of magnesium fully, what we need is at least 0.256 liters of HCl, or 256 milliliters. Okay, so now with solution stoichiometry, if we're to have this, and this is going to be a case where it's not going to be a one-to-one solution. And so what we see here is that iron nitrate, so here we need to remember a little bit of ionic bonding. So iron 2 nitrate, so Fe with 2 nitrates, which each have the charge of 1 minus, are going to react with potassium chloride. That's going to be KCl, both 1 to 1, because they both plus 1 and minus 1. Double replacement reaction that forms iron 2 chloride. That's going to be a solid precipitate, which we'll talk about that type of reaction later. So that's going to be our solid. And we're also going to have potassium nitrate remaining. Okay, what we need here is we need a balanced equation. Okay, so for every one of these, so Cl, we need 2 of those, so 2 KCl's, and to take care of the nitrates and the potassium, we also need 2 of those as well. So we have a 1, 1 to 2, 1 to 2 balanced equation. Okay, so if that's the case, we're looking for our limiting reactant. We have 22 milliliters of the 0.34 molar iron 2 nitrate, 33 milliliters of the 0.29 potassium chloride. Okay, and so very similar to what we did with regular stoichiometry, start with 1. Okay, in this case, I'm going to start with the iron nitrate. Okay, start with 1 and see how much of the other is going to be required to use it all up. And how much, what we're looking for there is a volume. So what volume of this KCl solution would we need in order to use up all the iron 2 nitrate in the solution that we have over here? Okay, and so since in this case, since we're actually calculating the number of moles in the process, the milliliters needs to be in liters. So 0.022 liters of the iron 2 nitrate. Okay, and then we have the molarity. So 0.34 moles is 1 liter. Liters is on top, so liters needs to be on bottom. So 1 liter of iron nitrate would be 0.34 moles of the iron nitrate. Okay, here we can account for our stoichiometry. Well, for every 1 mole iron 3 nitrate, we would need 2 moles of KCl. And where are we going to get the KCl? We're going to get it from a 0.29 molar solution. So in this case, we have moles of KCl. 0.29 moles is 1 liter. So 0.29 moles of KCl is equivalent to 1 liter of KCl. Okay, and so the amount that we would need is 0.0516 liters, or about 51.6 milliliters of that KCl solution. Okay, you need more of it, and its molarity is a little bit. You need more moles of it, and its molarity is a little bit lower, so you need a little bit more than twice as much in terms of the volume. So with what we have, you would need 51.6. What we actually have is 33. We don't have enough KCl. KCl would be our limiting reactant. Okay. Since this is a solid product, we can measure that in terms of grams. So from the product, just like regular stoichiometry, that's going to be based on our limiting reactant. Once that runs out, we can't do any more of the reaction. We're kind of capped out in terms of how much product we're going to get. Okay, so starting with our limiting reactant, well, 33 milliliters is how much of that KCl solution we actually have to use up. Okay, so 0.033 liters of KCl. Okay, and so each liter of KCl is going to give you of that solution that we're talking about is going to give you 0.29 moles of it. Okay, so for every 2 moles of KCl that you use up, you're only going to be able to get 1 mole of your precipitate, the iron 2 chloride. Okay, and that iron 2 chloride has a molar of 126.75. Okay, and so if everything goes to plan and we collect everything, the most we can get, our theoretical yield of iron chloride would be 0.606 grams of that precipitate. Okay, and the total volume present, okay, I'm not going to get to the next part, but the total volume present here, well, we just added 22 milliliters to 33 milliliters, and this is where the assumed volumes or additive come up. We'll get back to this again. We'll do the next part of this later. We would have 55 milliliters total, okay, assuming volumes are additive. That's all for today.